Welcome everybody. Welcome to the NZMS seminar. Can I just remind everybody to turn your camera and microphone off if you're not speaking. Speaker today is Shaun Cooper from Massey University, Auckland. Shaun studied at the University of Auckland and at the University of Wisconsin-Madison. If you don't know Shaun, I'd recommend you read the profile of him in the NZMS newsletter, which you can find online. He's going to speak to us today on the Rogers-Ramanujan continued fraction.
Hi, everyone. Thanks for coming. It's nice to see you all, even though I'm not sure who is there yet. Thanks also to Robert for the nice introduction and for organizing this series. So I was looking at the abstract for the talk, and it said just over 100 years ago, an unknown clerk from India wrote some letters to Cambridge mathematician G.H. Hardy. So he was unknown then, but of course we're talking about Ramanujan, and the letters were written in 1913, and now he's famous. He's no longer unknown. Here's a picture. So these people, this is neither Hardy nor Ramanujan. It's a couple of actors. On the left is Dev Patel. He's playing Hardy, and on the right, oh, sorry, I got that wrong, didn't I?
Yes, you did.
Let's try that again. On the left is Jeremy Irons, I think, who's playing Hardy, and on the right is Dev Patel playing Ramanujan. So this was made into a movie, came out about 5 or 6 years ago, and it was based on a book of the same name. So I won't go into the details about Ramanujan's life or any of that. As we say these days to students, watch the video. So we've got a nice movie available that we can watch about this. So carrying on about the abstract, it said about certain results in one of the letters. Hardy later wrote, "They defeated me completely. I had never seen anything in the least like them before." And he concluded that a single look at them is enough to show that
just over 100 years ago, unknown clerk from India wrote some letters to Cambridge mathematician G.H. Hardy about certain results.
Right.
Hi, I just wonder if someone's got their microphone on and some sound is coming back. Okay, I'll just carry on. So yeah, so some of the entries in some of the letters made such an impression on Hardy that he formed an opinion and sort of decided to do something about it. So what were these results that made such an impression on him? So they involved what's now called the Rogers-Ramanujan continued fraction, and this is what it is. So it's a fraction that by its name continues. You can see an obvious pattern here, q squared, q cubed. So those increasing powers of q just continue on down the pattern. And then there's, I hope this doesn't spoil it for anyone, but there's this q to the 1/5 on the top. So I hope that's not too upsetting for anyone. As with infinite series and infinite products, you can have discussions about what it means for it to converge. I'm going to skip over all of that and just work with it formally, and just mention that this fraction converges when q is less than 1. So here's one of the things that Ramanujan said in his letter. If you put q equals e to the power of -2 pi, then the continued fraction is an algebraic number, and here's its value. So that's one of the things in Ramanujan's letter. And right next to that entry, Ramanujan said, if you replace q with q to the 5 in that fraction and call that u, and let v be just the continued fraction itself, then u and v are algebraically related by this formula. So, you know, Hardy had no idea what to make of these formulas. He just concluded nobody could make this stuff up. It had to be good, is what he thought. Now, how do we get into something like this? So I think if we put q equals 1, this is something we've probably all seen before because there's a self-replicating part to this fraction. So if we take this 1 in the numerator and this first 1 in the denominator and just isolate those out, then starting again from this next position nestled in there, we get just another copy of the continued fraction in there. So that's r. Again, if we're calling this, whoops, if we call that fraction r. So quite easily, we can write down an equation for r. That turns out to be a quadratic equation. We can solve it. Assuming r is going to be positive, we take the positive solution and we get this value. So quite likely, this is something you've seen before. So the question is, how do we get from this back to what Ramanujan had with all these powers of q? Well, it's fairly easy to make this almost trivial generalization by putting an x into the continued fractions. This is not hard to do. And then when we read the 1 at the top and the first one, strip those off, and then start the fraction again from the x. If you take that x out as a factor, then you get another copy of the continued fraction below. So this one presents, it can be done the same way, presents no extra difficulty. And so solving this, you get a quadratic equation, you can solve it, and you get this value. So far, so easy. No problem so far. Then, and this is very, very likely what Ramanujan did, take what we had with these x's and pop in powers of q next to each factor of x. So we start with a q, q squared, q cubed, and go down and do the same sort of reasoning as we did before. And this time we pull off the ones, factor out the xq, and then look at what's left. And what's left is another copy of the continued fraction, but instead of variable x, it's variable xq. And so this time we get a functional equation for the continued fraction. And the Rogers-Ramanujan continued fraction that Ramanujan had was the special case x equals 1. So I just want to note that having this additional variable x allows us to create a functional equation. All right, now how are we going to solve this functional equation? So it's nonlinear, which makes it tricky. Now, physicists are really good at solving these sort of things. And actually, it's a bit like a differential equations course at undergraduate university. When you want to solve a certain type of differential equation, the teacher tells you a trick. I'll try this solution and plug it in. So the key, and this requires a bit of cleverness, a bit of insight, is to try a ratio of two functions, h of xq over h of x, and just substitute that into the functional equation. And we'll assume that h has a power series in the variable x. When you do that, when you substitute this, it's just like I said, just like for a differential equations course, you substitute this assumed solution back into the functional equation and see what you get, and it becomes linear. Then when you substitute the power series solution into the linear differential equation and equate coefficients of x to the n, so again, just like you do in cookbook differential equations, you get a two-term recurrence relation for the coefficients, and that can be iterated and solved pretty straightforward. And so that gives the coefficients Cn, so that gives the function h of x, and then the value of the continued fraction will be just a quotient of two of these series. So there it is. We didn't go as far as finding the constant term C0 because we don't need to, because it's a quotient, it cancels. So look, on just one slide there, we basically were able to fairly straightforwardly evaluate this continued fraction as a ratio of two power series in x. Sorry, it's just started raining at my place. I hope the noise of the rain isn't too loud. I'll speak a bit closer to the screen. So then we put x equals 1, and we get an expression for the continued fraction as a ratio of two infinite series. To go further, we're going to use something that are called the Rogers-Ramanujan continued fractions. So both of these series in the numerator and denominator turn out to have infinite product representations. Now, Ramanujan knew this. He knew this before he went to England, and it's written in his notebooks. While he was in England, Hardy asked Ramanujan if he had a proof, how to prove this, and Ramanujan admitted that he didn't. So Ramanujan went to the library. So in those days, universities had buildings which contained books, and mathematicians used to go in these buildings and study the books and look for things. And Ramanujan found that L.J. Rogers had encountered these identities and had proved them before. Ramanujan liked Rogers' proofs, and then Ramanujan found his own different proofs after that. So just a quick word about these Rogers-Ramanujan continued fractions. If you expand both sides and powers of Q and equate coefficients of Q to the n, they contain combinatorial information. So what it says is it says the number of partitions of an integer n into parts that differ by at least 2 equals the number of partitions into n into parts congruent to plus or minus 1 mod 5. So here's an example. On the left-hand side, we're working with the number 12. So n equals 12. On the left-hand side, that's all the ways of writing 12 as a sum of, so the rule is you can use whatever numbers you want as long as they differ by at least 2. So consecutive numbers are not allowed and repeated numbers are not allowed. On the left-hand side, they've got to differ by at least 2. And you can have 12 on its own. That counts. So that's what we get on the left-hand side, all the ways of writing 12 using parts that differ by at least 2. On the right-hand side, we're using a different rule. On the right-hand side, you can use numbers as often as you want, but you can only use the numbers 1, 4, 6, 9, 11, and numbers which are multiples of 5, 1 more or 1 less than a multiple of 5. So that's the rule on the right-hand side. Now, how many partitions do you get in each case? I didn't actually count them before this talk. The point is you get the same number of each type. So this example is for n equals 12, and the Rogers-Ramanujan identities imply that no matter what number you do, if you do the partitions into the 2 types, you get the same number. Incidentally, that's an analog of a interesting result of Euler, which says the number of partitions of n into parts that differ by at least 1 is equal to the number of partitions of n into odd parts. All right, so there's a lot of connections with a lot of different topics.
Is it one that differ by at least 1?
So just to sum up so far, we started with this infinite continued fraction. We slipped in a variable x and used functional equations, and we were able to write this continued fraction as a quotient of 2 infinite series. Then, by these Rogers-Ramanujan identities, we're able to write these infinite series as infinite products. So that's by way of an introduction to the Rogers-Ramanujan continued fraction. So I'd like to just carry on and mention some further properties of it. So I don't know if you've ever thought about this. What we have here, we've got 1 minus every power of q, 1 minus q, 1 minus q squared, 1 minus q cubed, keep going. Let's not worry about convergence, and let's just expand the brackets. So obviously, if you multiply the 1 from each brackets, you'll get a 1. If you take the q in the first brackets and then multiply by 1 in all the other brackets, you get a q. Similarly, you get a q squared. For q cubed, you could get a q cubed term in 2 ways. You could get that by multiplying the negative q by the negative q squared. So I've indicated that by the q to the 1 plus 2. And you could also get it by just the q cubed term on its own and multiplying by all the ones. And that comes with a negative sign. Actually, the q cubed terms are going to cancel. So do the q to the 4 terms. They're going to cancel as well. But the q to the 5 terms, there's 3 ways of getting them. You can get a q to the 4, q squared, q cubed, or just the q to the 5 on its own. So it comes with either a plus sign, depending on whether you use an even number of factors, or a minus sign, depending on whether you use an odd number. Here's a few more terms. Here's the q to the 6 term. I think that's going to be 0. And here's the q to the 7 term. So you can also get a q to the 7 by taking the q, q squared, and q to the 4. So that's all the different ways you can make a q to the 7. And I went a bit further. I went all the way up to q to the 50. And what you might notice from this is there's a lot of missing terms. Sorry, can you still hear me? It's raining really hard at my place, making quite a lot of noise. I'll just come a bit closer.
Yep, that's very good, Shaun. We can hear
Okay,
you.
thanks, Robert. Thanks. So there's a lot of missing terms, and it looks like the terms that survive are either a positive 1 coefficient or a negative 1 coefficient. Look, from this, it's easy to guess the pattern, and the pattern of the exponents turns out to be a bilateral quadratic progression. So these exponents turn out to be values of the quadratic j, 3j minus 1 divided by 2. So look, this is just guesswork. It's possible to do a detailed analysis of how you calculate these powers of 2, but an easier way is to generalize the product by slipping in a variable x and using functional equations like we did for the continued fraction. So that's called Euler's product, and there it is. Now, one of the things that we used to study in high school is anytime you get a quadratic expression like this is to complete the square. So if you complete the square on this exponent, that's what we're going to do. That requires adding a 1/24th. So there it is with the quadratic completed the square. And so that means we need to multiply by q to the 1/24th on the other side to do that. And the resulting function is called Dedekind's Eta Function. So actually I'm backing up a step. We're going to let tau be a complex number with positive imaginary part. And q is going to be e to the 2 pi I tau, so that q is less than 1. So the reason for studying this Dedekind Eta function is it has these incredible symmetries that are totally not obvious from anything we've talked about before. So I just want to mention them. So it turns out that if A, B, C, and D are any integers with determinant 1, AD minus BC equals 1, then the 24th power of the Dedekind Eta function, evaluated at this fractional linear transformation value of tau, is basically the same as the function evaluated at tau apart from this factor. So that's an incredible symmetry property that is not obvious at all from the construction, the way we've gotten it. In the business, we call such a function a modular form of weight 12. So the 12 is just referring to the power of C tau plus D. And just to make it clear, some special cases of this fractional linear transformation, the function's periodic with period 1, and also in reflection in the unit circle, it's almost invariant up to this factor tau to the 12. Okay, so just maybe memorize this slide and we'll come back and talk about this again. So that's Dedekind's Eta function, and it's this modular property. Hey, the next thing I want to talk about is dissections of series. So here's Euler's product again. Before we get to this, so dissections of series. So you've probably done this before, with the Taylor series for the exponential function e to the x. If you split e to the x into the even powers and the odd powers, what are the even powers in e to the x? I think that's hyperbolic cosine, isn't it? And the odd powers in the Taylor series for e to the x is the hyperbolic sine. So that's an example of a dissection of a series. What we're going to do with Euler's product is I'm going to do a similar dissection, but I'm going to dissect it into 5 parts according to the exponent modulo 5. So the black terms, the terms in black, those are the ones where the exponent is a multiple of 5. That's going to be the black terms. The blue terms, they're going to be ones where the exponent is 1 more than a power of 5. And the red terms, they're going to be the ones where the exponent is 2 more than a power of 5. What about the other 2 residue classes that are 3 more than a power of 5 or 4 more than a multiple of 5? Those terms, there turn out to be no such terms. That's pretty easy to check by just analyzing the quadratic here. So let's have a look at some of these terms. Let's look at the blue terms. So here I've written a few more of them. The first one is minus q. The next one is q to the 26. So these are all the terms whose exponent is 1 more than a multiple of 5. What are these terms? Well, we can factor out a minus q. So I did that. And now the factored series, they're all multiples of 5. Actually, does anyone notice anything about this series? What's the series here? I don't know if anyone notices. What have we got here?
Is it the e of q, but with q to the 25?
Awesome, thanks, Chris. So Chris has pointed out that the series we're getting here is precisely the series we started with, except q is replaced with q to the 25. So if you replace q with q to the 25 in the original series, that's what we're getting down here. Wonderful, thank you. So that's what it appears. It appears that the series we're getting is e of q, well, actually e of q to the 25. You know, that's a guess. And it's easy to prove. Okay, wonderful. Now you can do similar analyses for the black terms and for the red terms. And look, I'll just confess, for this talk, I just picked the easy one. For the black terms and the red terms, you've got to do a little bit more work, but so I'm going to just skip that. And so here's the result. So we're sorting these terms into 3 types. So the B terms, we've just mentioned those. The A terms, this is what it turns out, and the C terms. Now, what do you notice about these formulas, A, B, and C, apart from them being big? They've all got a 1 minus q to the 5j. They've all got that in common. So we can factor that out of the lot. And then what else do you notice? The remaining terms in the factorization for A of q look like the Rogers-Ramanujan continued fraction. Actually, this is the reciprocal. And the C, it looks like 1 over. Oops, it looked, sorry. And once you notice that, then this Euler's product, this 5 dissection, the A of q to the 5 is essentially 1 over the Rogers-Ramanujan continued fraction. The B of q, well, once you factor out the common factor, you just get left with 1. And you remember that factor q to the 1/5 that we had at the beginning in the Rogers-Ramanujan continued fraction. If you put that in, that neatly takes care of the q and the q squared that arise here. And we get this nice simple formula down the bottom here. So look, such formulas, they occur a lot. And I just want to just show where such a formula comes from. It comes from taking an infinite series and just splitting it up into 5 parts and seeing what they are. So here's the formula again, just written at the top of the page. And here's another formula you can get from it. I'm not going to go through it, but by playing around with complex fifth roots of unity, you get another such formula. And these can be written in terms of Dedekind's Eta function. So again, just remember R of Q is the Rogers-Ramanujan continued fraction. The Dedekind Eta function is this product. Now, what can we do with these formulas? So Dedekind's Eta function, I mentioned, had these symmetry properties. And I'm just going to mention one of them. And if we apply the symmetry property back to those formulas, they imply transformation formulas for the Rogers-Ramanujan continued fraction. And we had two formulas, so that's what you get. And I just want to remark that the fixed point, so what's the fixed point? If you put t equals 1 in this formula, if you put t equals 1, you can solve the resulting formula for r of e to the minus 2 pi. And that gives the evaluation in Ramanujan's letter. The second formula also has a fixed point. I think t has to be 1 over root 5 to get a fixed point from that. And you get an even more impressive looking evaluation. So that answers one thing. And just want to say another one. If you look at the two formulas together and replace t with 5t in the first equation, then you can use them to eliminate the term on the left, and you get an equation linking the right-hand sides, where v is just the Rogers-Ramanujan continued fraction, and u is r to the 5. Hey, be careful of this formula in the wrong hands. I've been teaching pre-calculus algebra course, and a lot of students in that course will, just distribute the fifth power through this, and that's sort of what it looks like you get on the right-hand side. Yeah, it is, but u and v are different things. So if you solve for v, then you get this really stunning looking equation. And you can also solve it for u. And so this is also interesting, just from a curiosity point. This is actually a quintic equation for u. And you can actually, with a parameter v, you can actually solve this quintic for u in terms of v just by rearranging the equations at the top. Okay. So that's a bit of background about the results that impressed Hardy so much. So look, I just want to go on ahead and mention some further results. I'm going to try and bring us up to some more modern times now. So I think this is not modern times. This is the Fibonacci sequence. So everyone has seen this before. This is slightly more modern. In 1978, Roger Apéry proved that the sum of the reciprocals of the cubes is irrational. If you've taught a differential equations course recently, or Fourier series, you'll know that the sum of 1 over n squared is pi squared over 6. And you may know a formula for the sum of 1 over n to the 4. So in contrast, the sum of 1 over n to an odd power, almost nothing is known about that. So it was a sensation when Apéry announced that he could prove this was irrational. In the course of his proof, he introduced two sequences. I'm going to just talk about one of them, but they're three-term recurrence relations, kind of like the Fibonacci sequence, except there are coefficients which are polynomials of degree 2. Just a single term is enough to start this recurrence relation. You just need the value of t of 0, because if you put n equals 0 in this equation, that would allow you to calculate t1 from t of 0. And when n is 0, the n squared is 0. So you don't need a value for t minus 1. One initial condition is enough to start this sequence. Now, obviously, Tn is going to be a rational number. So to get t of n plus 1, you're going to need to divide both sides by n plus 1 squared. And so based on that, we would expect the denominators in this sequence to grow like the square of n factorial. Now, much to the audience's surprise, Apéry claimed that these numbers are actually integers. And here are the first few. And this was met with quite a lot of disbelief. People didn't believe him. One way of showing this is to exhibit a formula for T of n. These are binomial coefficients. These are clearly integers. However, just point out, even if you know this formula and try substituting it into the recurrence relation to try and check it, it's actually pretty hard to do unless you're sophisticated and can think of some really good ideas. So it's not that obvious. Look, after Apéry's work, he created quite a sensation, and there was a lot in what he did, and some quite good mathematicians were interested in unpacking what he had done. So a few years after that, Fritz Berkes, I don't know how he got this, but he noticed if you started with the 5th power of the Rogers-Ramanujan continued fraction, and I'm just going to pull this other function z out of a hat. Now these each can be expanded in power series. So I've given just the first few terms there, and at least formally, you can expand z, this power series z, you can expand it formally as a power series in terms of q. You just get a triangular system for the coefficients t of n. And what Berkes proved is that these coefficients are exactly the coefficients that Apéry introduced. Right, so that's another connection where the Rogers-Ramanujan continued fraction just seems to be connected with all this stuff. So, of course, how Berkes did it is Berkes found a differential equation for z in terms of x, and I won't go on about that. I'll just mention that this differential equation, it has a lot of analogies with what are called complete elliptic integrals, and this is like a level 5 analog. The Jacobian theta functions, in this context, we would regard them as level 4. What was I going to say about this? Oh yeah, if we consider this function whose coefficients are given by terms in the Apéry sequence, then this power series satisfies some incredible functional equations. So we recognize this part as part of Ramanujan's letter to Hardy, and there's a nice quadratic functional equation where the squared symbol just hops onto the other term there. Now the 3-term recurrence relations were of interest, and Zagier picked this up a few years later. And Zagier wondered what other 3-term recurrence relations where the coefficients are quadratics, are polynomials of degree 2, when are they integer valued? So Zagier did a big computer search. So in those days, I think he did something like 100 million was his search space, and this was the realm of supercomputers in those days. And Zagier found that the only values of alpha, beta, and gamma, which produce integer values for the sequence, there are only 6 that he found. The first one here, 1131, that's Apéry's example. That's connected to the Rogers-Ramanujan continued fraction. So these sequences all have formulas involved with as binomial sums. It's an open question as to whether there are any more. So here the recurrence relation, the polynomials are degree 2. So a bit after that, I had a look for similar recurrence relations where the coefficients are polynomials of degree 3. So I had some good reasons for doing this. It's not as if I just got out of bed one morning and decided to try this. It was a result of all sorts of, noticing coincidences and stuff, and then deciding to do a big computer search. So I had a look, and I found just 3 examples. And one of them turned out to be classically known. And I just want to tell you a little bit about the first one that's here. So there it is. So I was interested in knowing whether it has a similar modular parameterization like Burke's had. So first of all, there's a formula for the coefficients, which reveal clearly their integers. And so here's what I found. I did all this experimentally, numerically. If Z is this, the square of this double power series, and X is this combination of infinite products, then when you expand Z as a power series in terms of this variable S, X, the coefficients are these terms S. And what you'll notice a definite 7. There's sevens everywhere in these formulas. 7, 7 squared. The discriminant of this quadratic, b squared minus 4ac, is minus 7. So this is a level 7 analog. So whereas Rogers-Ramanujan is level 5, this is level 7. And just the other sequences that I found, the classical one, there's a level 10 analog, and the other one is a level 18 analog. What other properties? If we go back to Apéry's sequence again, so here are the numbers. One of the first questions you might have had is, what divisibility properties do these numbers have? You know, are they prime numbers? Are they divisible by something? So surprisingly, there are a lot of properties like that. And I'll just tell you about one of them. Let's take P to be any prime and N any positive integer, and write down the base P representation of N. So we're writing N in base P, and N0, N1 up to N are going to be the digits in the base P representation. Then it turns out that the nth number in this Apéry sequence is congruent to the product of the N0, N1 up to NR terms in the Apéry sequence modulo the prime. So this is called a Lucas property, after Lucas, who more than 100 years ago noticed that the binomial coefficients have a property like this. So it turns out that that all 6, so the other 5 sequences of Zagia, they all have a property, they all satisfy the same property. So that's interesting. Another type of topic that is under current investigation is these Apéry numbers turn out to be coefficients of x to the n, y to the n, z to the n. They're called diagonal coefficients in the series expansion of these multivariate rational functions. I just mentioned this one, and that's a topic of ongoing work. So I just mentioned this forthcoming paper of Gorodetsky. He's got a very, very nice survey of not just Zagia's 6 sequences, but also the 3 that I studied, and there's a few other ones like that. I don't know if there are any analysts here, but I'll go over this one really fast. Hi, Eric, I think your microphone might be on. Back to the 3-term recurrence relation. Here's another 3-term recurrence relation, basically using the same alpha, beta, gamma, but souped up so that the coefficients are degree 3. Then it turns out that the square of the generating function for the Tn's can be expanded as a power series involving the Sn's. This is an absolutely incredible result. There are not many power series that you can square exactly in mathematics. Okay, you can square e to the x. That's e to the 2x. You can square the binomial series, 1 minus x to the n. You can square that. But apart from those elementary functions, there's not many functions, not many series you can square and write them out exactly. In fact, probably the last big one to be found was due to Clausen, and that was in 1828. And there's a second way you can square it. You can expand in terms of this other power series variable. So these are incredible results. They can be proved quite easily, though, by constructing the differential equations that each side satisfies. So that's actually that's incredibly tedious to do by hand. So you would do that by computer, using a computer to do the changes of variables. So these beautiful results were found by Zuderlin and co-authors about 10 years ago, and they've opened up a lot of things. Now, I'd like to just wrap up briefly. So look, there are some other continued fractions in Ramanujan's work. So here's another one, and this one can be written in terms of Dedekind Eta functions, and this one's got a sort of a six-fold aspect to it. So we saw that the Rogers-Ramanujan continued fraction had a level 5 aspect. We've seen a level 7 one, so this one is level 6. And pretty much all of the things I've talked about that you can do for the Rogers-Ramanujan continued fraction, you can do the same thing for this guy. I'd like to mention a couple of references. There's a very beautiful paper by Bill Duke in the bulletin. It's a little while ago now, but he's got quite a different emphasis from what I've talked about in this talk. So he goes into much more into the modular forms aspect. And hey, we all know with complex numbers, if you're talking about complex nth roots of unity, you know, the complex third roots, for example, we tell students they lie on a unit circle. In fact, they lie on a regular polygon. So Duke talks about how certain values of the Rogers-Ramanujan continued fraction are connected with the isosahedron, for example. So that's a very nice talk. And look, can I rather modestly also recommend this book, which has got a detailed account of levels 1 through 12. And chapter 5 is all about level 5, which is about the level of the Rogers-Ramanujan continued fraction. Here's the last slide. So I just want to finish with one more formula that hopefully Hardy and Ramanujan would have liked. Here's the Rogers-Ramanujan continued fraction again. Then the logarithmic derivative of this rational function of the 5th power of the continued fraction can be expressed as a power series in terms of this other rational function. And the coefficients are binomial coefficient 2n choose n times these Apéry numbers. Hey, that's the end of the talk. Thanks for your attention. Hope you survived all that.
Thank you very much, Shaun. Very good. Are there any questions? If you have a question, please just unmute your microphone and fire away.
I've got a question, if that's all right.
Please go ahead.
Great talk, Shaun. Do you want to say a little bit about the q to the 1/5, which gets put there, which you told us to not be disturbed by? Do you want to explain a little bit more why you need to put that q to the 1/5?
Yeah, so the q to the 1, thanks, Stephen. So I might just wave my hands a little bit about it. So I did show where the q to the 1/24 comes, you know, I used some cheap argument. I said, look, just complete the square in some quadratic and makes the q to the 1/24. So the q to the 1/24 for the Dedekind Eta function, having that gives the modular properties. And so the q to the 1/5, that gives the modular properties here. So that's the real reason. The other reason is like the cheap explanation is when we did the 5 dissection of Euler's product, and we took all the terms in the power series and we divided them into the 5 types. And so we had terms with a q and a q squared. That all gets absorbed by that q to the 1/5. That's another way. That's maybe a cheap way. If you just try and write it in the sneakiest, or not the sneakiest, the most elegant, tidiest notation, you would be forced to put in the q to the 1/5 just to make that result look as clean as possible. But the real reason is it gives them modular properties. So I hope that's all right.
I have a question. If there are not. Hi, thanks for the talk. My question is, it looked like you had periods of an elliptic curve and differential equations governing the periods for a family of elliptic curves, if I looked at it correctly. And then it looked like maybe you expanded one solution in terms of another solution. Is that what happened?
Yep, that's exactly right. So this, and in fact, that's what this expansion at the bottom is. This expansion at the bottom, the left-hand side is a weight 2 modular form, and this business in the brackets, that's a modular function. And there's a general result. If you've got a modular form of a certain weight, and you've got a modular function, and all the levels, all the groups and stuff all work out, then the modular form satisfies a differential equation of a certain order. And so that's what's going on there. This is a general audience, so I didn't want to go there, but that's exactly right. And the first one we did, it's a Burker's result, the one that we wrote out explicitly. That's the expansion of a weight 1 modular form in terms of a modular function. Yeah, so these things all generalize, and this is like one of the first sort of non-trivial examples for, the groups are like gamma 1 of 5 or something like that.
Thanks.
Yeah, you're welcome. So Bill Duke's paper, I think, will have more on that.
Shaun, you gave an example of an application to partitions and these identities between different types of partitions. Is that also a sort of sporadic phenomena, or are there lots of results like that?
Thanks, Robert. So yeah, that's been generalized to the untold degree. Yeah, so these days there are lots and lots of results of partitions. Yeah, these ones are the sort of the most elegant ones. And yep, so to answer your question briefly, yes, there are. So that was back in the Rogers-Ramanujan, back in the, but you just reminded me there's something else I can say about these. Yeah, so this result. So this is a combinatorial interpretation of these Rogers-Ramanujan identities. I might answer your question a different way by saying these Rogers-Ramanujan identities have been rediscovered by lots of people. Rogers discovered them first. Ramanujan discovered them independently. I think Schur discovered them. Rodney Baxter, the Australian mathematician physicist, he also discovered these Rogers-Ramanujan identities independently in work he was doing on the hard hexagon model. So that's another place where these things arise. So that's not quite your question, but yeah, these particular Rogers-Ramanujan identities show up a lot in a lot of places. Let me just leave it at that.
The other thing your talk reminded me of is there was a thing in the news a few years ago where some Israeli teenagers did what they called applying artificial intelligence and supercomputers to discover new continued fraction identities, which the claim was that some of them were genuinely new. Is that at all related?
That's a really wonderful account, and yeah, I looked that up. So that is continued fractions as well. So individual numbers like e and pi, based on their properties and things, you can write those as continued fractions involving numbers. Where they come from, a lot of them, is they come from 3-term recurrence relations for underlying hypergeometric functions. So the result that these Israeli, I think they were young people, quite youngsters, did is quite extraordinary. I'm going to duck and do something else. I don't know if anyone knows, but also recently last year, some also teenagers discovered a two-term recurrence relation that produces every single prime in ascending order. So here's the two-term recurrence relation. Fn is some function of Fn minus 1, and Fn is the nth, the floor of Fn is the nth prime. A totally incredible result. And it's not a fast one. It's not some trivial trick. You do need to start with this irrational number, F1, which of course, that gives the game away a little bit. Somehow this irrational number contains information about every single prime. So if you start with this irrational number and calculate Fn by this two-term recurrence relation, then the floor of Fn is the nth prime. An incredible result. So this was discovered by, this is in the monthly, I think. This is the American Mathematical Monthly. So 4 of these people, I believe, are teenagers from Argentina. And one of them, I think James Grime, I think he's a mathematician at Cambridge. He helped them formalize and write the paper. So, every talk should have a take-home message, even if it's not about the material. So there we go. That's something that we can look up, especially any number theorists that might be here. We should know about this. Thanks, Robert, for mentioning that.
So thanks, Shaun. Are there any further questions before we wrap up? Well, I still haven't worked out how to do virtual applause. We could all unmute. We could all unmute. Would that work if we all unmuted our microphones and gave Shaun a round of applause?
Thanks, Robert. And
thank you, Shaun.
Thanks for coming, everyone. Thank you.
Thank you, Shaun.
Thanks, Shaun. Great talk.
Thanks, Henko. Thank you. Nice to see you. Thanks.
Thanks.
Thanks, Bernd. Hey, nice to see you.
Yeah, likewise. Hopefully sometime in real life again.
Yeah, when we get back to a lower level. Yeah,
yes, please.
Thank you, Shaun.
Hey, hi, Mohsen. Hey, thanks for coming. Glad you made it.
Thank you. Could you please send me that article you showed to me? It's a prime representing constant.
I will. I'll do that right away. Sure will.
Yeah. Thank you so much.
Thank you, Shaun.
Hi, Graham. Nice to see you. Thanks for coming.
Thank you. Thank you. Cheers. Goodbye.
So, Shaun, the announcement of your talk has seems to have led to a flurry of interest in the Zoom seminar. So it looks like we'll be having one every 2 weeks, at least through to January. We've got some lined up now. So.
Oh, that'd be awesome. That's terrific. Yeah. Nice one. I look forward to them. Thanks for organizing this. It's a great thing to do.
Takes our mind off the daily COVID numbers.
Yeah, and the daily first year teaching and stuff as well. It's nice to nice to do something really interesting. So it's good.
I can't promise you I'll buy your book, Shaun, but how about if I get it out of the library? Would that be acceptable? That'd
be wonderful. I think you can probably click. We might have an online version. I think you don't even need to go into the building if you.
Every time I suggest a book to the library, they always buy the ebook these days anyway. So
It's actually probably more
Some reason
useful
they
for people. Yeah, I mean, I don't know about you, but if I want to look something up, I'm quite happy just to do it on my computer. And if I can find what I need in the book, it depends, isn't it? There's pluses and minuses of each one.
I've never actually read an ebook all the way through, but maybe one.
All right. Hey, I think we're done. I might log out now. I think we're down just to the last handful of participants.